Swayam Prabha. Digital India. Educated India.
composition also changes. So these two situations we are going to model. Now when you deal with the second aspects, like when you talk about mechanism of mixing process in the second approach, so this mixer process is always irreversible, because this mixer is formed spontaneously and the work input from the surrounding, that means if you want to separate the gases out of this mixture, then we would be requiring work input from the surroundings, and this is never possible. So we call this process to be an irreversible process. So we need to calculate, that means when you deal with the thermodynamic properties, that means the parameter that needs to be going to evaluated for irreversibility calculation is the entropy. The irreversibility, why irreversibility term comes into picture? Because we said that the individual components that are initially separate. So when they are initially separate, they may be at different temperatures, they may have different pressures, and they are also distinguishable from one another. That means different gases. So because of this reason, the process is irreversible nature. Now let us target them one by one. First one is that we consider a process, mixing process at constant compositions. So here if you look at this picture, we have a mixer at state 1 and state 2. So what it means is that initially the mixer is formed with J number of gases with their mole fractions N1, N2 and Nj, and it is at initial pressure and temperature T1 and P1. Now there is a change of state that happens, but at same composition. The composition do not change, but what changes is the pressure and temperatures. So because of this change of state, we will land off in the change of energies. Like we have initial internal energy U1, will have final internal energy U2, we have initial enthalpy H1 and final enthalpy H2, initial entropy S1 and final enthalpy S2. So our previous studies or previous expressions enables us to calculate the changes in the internal energy of the mixer during the process. So if you can calculate that what is U2 minus U1, that U2 change in the internal energy of the mixture between state 2 and 1, we can represent in its molar value, that means molar specific internal energy multiplied by its mole fractions. So this molar value has to be considered at two different states, that is temperature T2 final state and temperature T1 initial states. By doing so, you can find out change in the molar specific internal energy, which is the summation of the internal energy of any of an individual component I from state 2 and state 1 multiplied by its mole fraction. So if you make summation of for all the components, we can calculate the total change in the molar specific internal energy. Similar philosophy can also be applied to calculate the change in the enthalpy, molar specific enthalpy. Then moving further, we can also calculate the change in the entropy. But when you calculate the change in the entropy change requires that the entropy change is to be calculated at pressures for the each component I will have its own partial pressure, and this partial pressure is going to be different for the state initial state and final state. So at the initial state, the partial pressure for the component I is Pi1, and in the final state 2, the partial pressure for the component I is Pi2. But and there also done the temperature of the component I, that is initial state at is T2 and final state at T2 and initial state at T1. So these particular expressions can be represented in summation form, that S2 minus S1 in terms of the molar specific change in the entropy multiplied by its mole fraction. Now here the important aspects that we need to calculate, that what is this delta SI, that is for component I we want to find out molar specific internal energy, and by definition or the entropy calculation earlier, this has to be calculated with the concept of absolute entropy. Now when you deal with the absolute entropy, the choice of pressure is meaningless. So we have to calculate the absolute entropy for the component I at temperature T2, absolute entropy for the component I at temperature T1, then pressure effect will come, difference this of these two minus R bar ln Pi2 by Pi1. Now when I say this is a constant fixed mixture composition, Pi2 and Pi1 ratio will have same ratio P2 by P1. So this is how you have to calculate. This number gives the change in the molar specific entropy as a function of absolute entropy change and minus R bar ln P2 by P1. This is one way of evaluation. Other way of evaluation is that we can also calculate the same things through CP calculations. So delta S we can write is Cp times ln, by definition entropy change is Cp times ln T2 by T1 minus R ln P2 by P1. Then this Cp for the component I is represented by Cp bar Pi, and knowing this value we can use these expressions, because we all know that what is the final state T2 and P2 and what is the initial state P1 and T1. Then we will move to different case studies. First case is the compression of an ideal gas mixture. So here the compression of an ideal gas mixture means that, for the sake of an example, you can say that we have a piston cylinder device which contains certain gas. Here I have written as some mass of carbon dioxide and some mass of nitrogen, and this mixture is being compressed by this piston. Now when it is compressed, the initial state of the mixture, which is state 1, moves to state 2 in a polytropic process with some polytropic index, let us say n is equal to some value of n. Now when on such a things there, then how you are going to calculate the overall properties of the mixture. So there are certain assumptions that we are going to say is that the changes in the kinetic energy and potential energy between initial and final state is ignored. Each component of the mixtures behaves as if it were an ideal gas occupying the entire system volume at mixture temperature and pressure. Then mixture composition remains constant during the compressions. Having such these assumptions, we can write the polytropic equation PV to the power n is equal to constant. Side by side we can find the pressure, temperature and volume relations between initial state and the final states. Then work transfer, since it is a compression process, work transfer can be calculated as integral of PdV. Then from this equation we can calculate work transfer. Since it is a closed system analysis, so we can find out the energy balance equation for the closed system, Q is equal to delta U plus W. And of course we know from Q and W we can also calculate the internal energy change, U2 minus U1. This U2 and U1 has to be calculated with respect to state 2 and state 1 by knowing the composition of each individual gases. The next example that we are going to discuss is the expansion of an ideal gas. So when I say expansion, one typical expansion process, as you can see, that a gas from its initial state P1, B1, T1 expands in a nozzle. So this is a schematic diagram of nozzle. So the characteristics feature of the nozzle, it increases, the flow expands in the nozzle, and as a result of which, and the process in this nozzle is normally treated to be isentropic process. Here in our previous analysis we used to say that only one gas expands in the nozzle. So analysis of the treatment was little bit different and simple when you dealt with the control volume analysis for the nozzle. But here a mixture expands in the nozzle. when a mixture expands, one thing we are assuming that they have constant composition. Mixture composition remains constant, and the state of each component is defined by its initial, by its temperature and the partial pressures. Same way we also can say that kinetic energy and potential energy effects can be ignored. And the process in a nozzle is typically considered to be an isentropic process. So, isentropic process means the change in the entropy between state 2 and 1 is 0. So, we can calculate S2 bar minus S1 bar, and that is nothing but is its mole fraction of component 1 multiplied by delta S bar for the component 1 plus Y2 into delta S bar of S2. And again, if you can recall our previous relations, delta S1 bar and delta S2 bar can be calculated with the concept of absolute entropies and partial pressures of each gas. And normally when we use the word nozzle, we used to say that it has to increase the flow velocity. So, the flow velocity is associated with the enthalpy calculations, where flow velocity is calculated with respect to enthalpy information. And of course, here we are going to use another relations in terms of the molecular weight, and this molecular weight is required for calculation of enthalpy, and enthalpy and flow velocity relations can be related as H1 minus H2 plus B1 square minus B2 square by 2 is equal to 0. And this model was done for an energy rate balance for an one inlet and one exit control volume at steady state. Next type of mixing, we call this as a adiabatic mixing at constant volume. Now, in our previous study, previous two cases, we have seen that the mixture was at constant compositions, and during this process of change of state, the composition do not change. Okay. But and the mixture expands or compress and during the change of state. And now we will consider a situations where the components are initially separate, and after certain situations they form a mixtures. One such case is adiabatic mixing at constant volume. So, if you look at this particular figure, it says that there are two gases, nitrogen and oxygen, and they are separated by a partition, and entire system is insulated. That means insulated means there is no heat transfer into or out of the systems. Now, this partition, or now you want trying to mix. So, when we are trying to mix, we allow this partition to come to open through this valve. Now, when this opens, the initial state of nitrogen and initial state of oxygen is going to change. So, at what does the consequence could be? The initial mole fraction of oxygen could change, oxygen, and the number of moles of this is going to change. And since they are at different pressures, at steady state there will be pressure equalization, and we will have an effective temperature of the mixture. So, to analyze such a things, we assume certain things like system is taken to be the combination of both the gases, and each gas behaves as an ideal gas. The final mixture also acts as an ideal gas. And another important aspect is that each mixture component occupies total volume. That means after the valve or this partition is over, each mixture components occupies the total volume and exhibits the mixture temperature, and they have the common uniform temperatures. There is no change in the kinetic and potential energy. So, having said this, we are going to analyze this particular case with energy balance and entropy balance equations. So, energy balance, we have used the first law which talks about the information. Since it is a closed systems, we have to deal with the internal energy delta U plus W, and this equation there is no heat transfer and work transfer. So, U2 minus U1 will be 0. Now, let us see how you are going to calculate this U2 and U1. So, if you say U1, that means U1 means you have to calculate this U1 value based on its molar composition. So, that means if it is gas 1, its number of moles is Ng1 and multiplied by its molar internal energy for gas 1 at temperature Tg1. And similar way, the internal energy for gas 2 can be calculated by its number of moles and its molar value of specific internal energy at temperature Tg2. So, this way we calculate the total internal energy of the systems at system, and then similar way we can calculate the total internal energy at the when it goes to the change of state. So, from these things we can rearrange these equations, and also internal energy is a function of specific volume. So, you can introduce the specific volume of the gas. From mole fractions, from mass and mole, we can get the molecular weight. So, using these relations, ultimately what we are going to target, that when the final state is reached, what is the final temperature T2, what is the final volume V and final pressure P. So, this is how the energy balance equation will give you all these numbers. Then we have to think about entropy balance equations. That means here it is a closed system entropy balance, S2 minus S1 is equal to integral of dq by T 1 to 2, and for these situations dq goes to 0 because there is no heat transfer. So, it will give you the entropy production through this change in the entropy. Now, S2 has to be calculated at means total entropy at state 2 has to be calculated with respect to final pressure, temperature. S1 has to be calculated with respect to at the initial state of this mixture. Now, if you look at here, now S1 if you calculate, it is a function of its number of moles of this gas and molar specific internal energy, which is a function of Tg1 and Tg2 for the gas 1, and it is function of Tg2 and Pg2 for the gas 2. Similarly, when you go to the final state, final pressure of the gas 1 will be mole fraction of Y1 into P2, and mole fraction of for the gas 2 would be Y2 into P2. P2 is your final pressure, which is this. Then by putting this will give you an expressions of entropy production during this meshing process. Now, while doing so, we can also bring out this change in the entropy, which is a function of Cp and R. So, these relations has to be used. So, basically when you solve the problem and try to find out how I am going to introduce the property values, then the picture will be more clear. So, we will discuss them down the line. Okay. And the other one is that adiabatic mixing of two streams. So, here this is a situation where mainly we come across this particular concept when you deal with the psychromatics, when air and water vapors are mixed. So, when I say adiabatic mixing of two streams, like I can assume that something that there is a passage, two streams or two gases from state 1 and 2, they come and they mix, and finally the mixture goes to at state 3. So, we can say gas 1, gas 2, and it is forms as a mixture of two gas. Conditions of gas 1 may be P1, T1, and condition for gas 2 may be P2, T2, Mg1, Mg2. Gas 3 could be final pressure P3, T3 and Mg3, and it is a mixing process is adiabatic. So, there is no heat transfer into this medium. Now, for this situation we have to write down the mass balance and energy balance simultaneously. So, you have to consider this mass balance, molar mass of the mixture. So, this will give you the mole fraction and mass fraction of this mixture. In addition to that, we also, I forgot to mention, we have to consider also energy balance equation. So, mass and energy balance equations need to be taken together to calculate the states of thermodynamic states of the mixture. So, thermodynamic state of mixture is to be calculated with respect to is calculated through mass balance, mass and energy balance. Now, apart from this, we also need to find out the entropy balance, and because it is an adiabatic mixing process and process is irreversible. So, entropy balance will give you what is the entropy production rate. So, this is also we have to use the similar philosophy, that what is the entropy at state 1 for the gas 1, and this is to be evaluated at gas pressure and temperature and pressure for the gas 1. For gas 2, it has to be evaluated at its corresponding pressure P2 and T2, and after the formation of the mixture, the composition of the components may change. So, that is what we will land up having the mole fraction for the gas 1 and for mole fraction for the gas 2. And once you know this mole fraction and final pressures, the entropy will be evaluated at that temperature and pressures. By inserting this value, we can calculate the entropy production term. Now, here important thing that need to be find out for entropy calculations, the change in the entropy for the gas 1 from its final state to initial state, we need to require the concept of absolute entropy, and these absolute entropy values can be used to find the entropy change for respective gases. So, here it is an example of two streams. So, there are situations you can have multiple number of streams, and for each streams these terms needs to be evaluated. Okay, this is all about the 4 different important cases that is going to be considered for the mixing analysis. Now, based on our analysis for the discussion for the lecture today, we are now going to solve some numerical problems which is nothing but the 2 different case studies what we have studied. First one is mixing process at constant compositions. So, when I say constant composition, I will use the same example or same problem which figure which has been given in the earlier discussions. So, we will be using the values directly here. Now, let us see how you need to go about while solving the numerical problems. So, here the problem statement is that we have a mixture of 0.3 kg of carbon dioxide and 0.2 kg of nitrogen, and they are getting compressed. This mixture is compressed from its initial state, which is 1 bar 300 Kelvin, to a final pressure. So, final pressure of the mixture is 3 bar, and this process, this is a compression process, that means we go from initial state to final state through a polytropic process, and this polytropic index is given in this figure as n is equal to 1.25. So, this polytropic equation Pv to the power n is equal to constant, where n we say it is 1.25. Now, if this is the situation, let us see how you will go about. So, let us start the solutions. So, the first question that was asked, we have to find out the final temperatures. We are given with the final pressure, but we are not given with the final temperatures. Now, to do this final temperature calculations, now for a polytropic process, we can write, which satisfy Pv to the power n is equal to constant, we write this as T2 by T1 is equal to P2 by P1 to the power n minus 1 by n. So, we are given with P1 1 bar, P2 3 bar, T1 300 Kelvin, n 1.25. So, by inserting this number we get T2 is 374 Kelvin. So, we get the final temperature as 374 Kelvin. Second part, we are going to evaluate what is the work transfer. So, work transfer is normally given as integral of P dV from 1 to 2. So, you have this equation given where Pv to the power n is equal to constant, which implies P is equal to C divided by V to the power n. Now, after this integration, we will have the final expression for work transfer is m times r bar by m. So, it is nothing but mass into T2 minus T1 divided by 1 minus n. Now, here we do not know what is the mass and we have to find out what is the mass. So, total mass would be 0.3 kg plus 0.2 kg, that is 0.5 kg. And what is the molecular weight of the mixture? That molecular weight of the mixture m would be mass divided by number of moles. So, here we have NCO2 plus NO2. Now, what is NCO2? NCO2 is equal to mass of CO2 divided by its molecular weight of CO2. So, mass of the CO2 is 0.3 and molecular weight of CO2 is 44 and this number is 0.0068 kilomole. Similarly, N2, mass of N2 divided by molecular weight of N2. This is mass is 0.2, molecular weight is 28. This value is 0.0071 kilomole. So, thus we can say what is the molecular weight of mixture is equal to m. M is total mass 0.5 divided by 0.0068 plus 0.0071. This value is 35.97 and this is nothing but we call this as a apparent molecular weight. Weight of mixture. So, we know all the numbers, so we can insert the values to calculate what is work transfer. Work transfer would be 0.5 R. What is R bar? R bar is 8314 or you can say 8.314 kilojoule per kilomole Kelvin and 8.314 divided by 35.97 into T2 minus T1, 374 minus T1 is 300, entire thing divided by 1 minus 1.25. So, when we evaluate this number, we get W is equal to minus 34.2 kilojoule, which implies that compression work. Negative sign implies that it is a compression work. Okay. So, now next part is that we need to calculate the heat transfer. So, for heat transfer we need to go for this heat transfer by first law. So, you can write Q is equal to delta U plus W. W from our previous expression we have already calculated, that W is minus 34.2 kilojoule. Now, to calculate delta U, and we need the information for mixture at its initial state and final states. So, let us see how you are going to evaluate delta U. Delta U is, you say, U2 minus U1. What is U2? That is number of moles of CO2 into U bar CO2 at temperature T2 minus U bar CO2 at temperature T1 plus, that is U2. Now, U1 is NO2, N2, number of moles of N2. So, U bar N2 at state 2 minus U bar N2 at state 1. So, here we require the information about the molar specific internal energy at two different temperatures. So, we need to recall or use the thermodynamic data table. And this is available in any of the thermodynamic books towards the end. So, in this case we need to find out 4 numbers for N2 as well as CO2. So, let us see what is U bar CO2 at temperature T2. Temperature T2 final temperature is 374 Kelvin. This value is 9198 kilojoule per kilomole. Then U bar CO2 at 300 Kelvin. This value is 6939 kilojoule per kilomole. Then U bar N2 at 374 Kelvin. This value is 7770 kilojoule per kilomole. U bar N2 at 300 Kelvin. This number is 6229 kilojoule per kilomole. So, we already know what is NCO2, that is 0.0068 kilomole, NN2 0.0071 kilomole. So, all the data we have, then we can get this delta U as 26.3 kilojoule. Hence, Q would be minus 7.9 kilojoule, which means that compression increases the temperatures, which means heat transfer from the system. Okay. And last one is we need to calculate the change in the entropy. So, the entropy change, if you want to calculate, that is delta S, we can use it as NCO2 delta S bar CO2 plus N2 into delta S bar N2. So, important thing you need to calculate here, this delta S for CO2 and L2. So, this value has to be calculated with respect to absolute entropy concept. for which the absolute values need to be calculated at given temperature only. So, for that we can say this is represent S bar O for CO2 at temperature T2 minus S bar O for CO2 at temperature T1 minus R bar ln P2 by P1. Similarly, we can write it delta S bar for N2, that is an entropy, absolute entropy for N2 at temperature T2, absolute entropy for N2 at temperature T1 minus R bar ln P2 by P1. So, these values needs to be calculated. So, again similar way we can note down this number from the data table book, that is S bar O CO2 at 374 Kelvin. This is 222.47 kilojoule per kilomole Kelvin. S bar CO2 O at 300 Kelvin, this is 213.91 kilojoule per kilomole Kelvin. Then for N2, S bar N2 O at 374 Kelvin is equal to 198.1 kilojoule per kilomole Kelvin. S bar O N2 at 300 Kelvin, this number is 191.7 kilojoule per kilomole Kelvin. So, we know all the numbers. Of course, we know P2 as 3 bar, P1 1 bar, R bar 8.314 kilojoule per kilomole Kelvin. So, by inserting these numbers we can get that what is delta S is equal to minus 0.0231 kilojoule per Kelvin. So, mixing process, it is a negative quantity, so that means entropy during the mixing, since heat transfer is negative, so you also get entropy as a negative value. Okay. Now, in the next problem we are going to talk about a situation in which a dry air is mixed with a stream of oxygen, and this mixing process is an adiabatic process. So, it is a case of adiabatic mixing. So, adiabatic mixing means we have two streams, they come in contact with each other. Stream 1, case state 2 and state 3. At state 1 we say it is air and it is coming at flow rate. So, flow rate means area times velocity. I will multiply this as 100 meter cube per minute. P1 1 bar, T1 32 degree centigrade, that is 305 Kelvin. State 2, it is oxygen, and oxygen, it is condition is P2 1 bar, T2 127 degree centigrade. So, this is 400 Kelvin, and the final mixing stream, that is we say mixed stream. The mixed stream has a condition P3 is same pressure 1 bar, but temperature T3 is 47 degrees centigrade. So this is 320 Kelvin. Final temperature is comes as 320 degree Kelvin, which means that composition of air and oxygen are adjusted together so that final temperature is reached. Now to do that, we need to recall two things. One is the mass balance and energy balance. And this mass balance and energy balance will give you the information about the mass flow rate and mole fraction. How do you do that? So first thing is we have to find out what is m dot A1, which is area AB1 for the stream 1 divided by its specific volume of air. And to calculate the specific volume, we need to require the information like this. So we have molecular weight of air, that is 28.97. We know temperature T1 32 or at 305 Kelvin, P1 1 bar, and then R bar is 8314 joule per kg mole Kelvin. So this will give you specific volume VA1 and as 0.875 meter cube per kg, and we have AB1 area times volume flow rate 100 meter cube per minute. So these two information will give you as mass flow rate of air, that is MA1 as 114.3 kg per minute. So we have mass flow rate of air. We do not know mass flow rate of oxygen. We also do not know mass flow rate of mixed stream. Now when I say mixed streams, I can assume that mass of air m dot A1 is equal to m dot A3 and m dot O2 is equal to m dot O3. So this is the things. Then we have to consider the energy balance. So energy balance we can write as m dot A HA at temperature T1, that is for air. So m dot oxygen, enthalpy of oxygen at temperature T2 minus, that is enthalpy, inlet enthalpy. Exit enthalpy will be m dot A HA T3 plus m dot O HA HO T3, that is equal to 0. So by putting these conditions, we write this will give you m dot O is equal to m dot A HA T3 minus HA T1 divided by HO T3 T2 minus HO T1. So we require enthalpy information at different temperatures. So we say HA, air at temperature T3 320 Kelvin. So this number is 320.3 kilojoule per kg. HO, oxygen is also same temperature 320 Kelvin. This value will be 9325 divided by molecular weight of oxygen, kilojoule per kg. You remember you need to find out enthalpy in kilojoule per kg. Similarly, HA for 305 Kelvin, that is inlet state. For air, this value is 305.2 kilojoule per kg, and HO for at the inlet state 400 Kelvin, this is 11711 divided by 32 kilojoule per kg. So, this data we get from the thermodynamics, any thermodynamic books towards the end of these chapters or books. So, after inserting these numbers, we get m dot O as 23.1 kilojoule per minute. So, this gives the information about mass flow rates. Now, once you have mass flow rate, then we can get mole fraction. Secondary information you require mole fractions. So, mole fractions, that is n dot A is equal to m dot A by ma, and m dot A is mass of air 114.3 divided by molecular weight of air 28.97, this is 3.95 kilomole per minute, and NO2 is m dot O2 divided by molecular weight of O2, that is 23.1 divided by 32, it is 0.72 kilomole per minute. So, total number of moles N is equal to this plus this 4.67 kilomole per minute. Then Ya, mole fraction of A is n dot A by N 0.846, Y dot O2 is equal to n dot O2 divided by N, this is 0.154, and last part is entropy production. So, entropy production equation is written through the control volume equation, and that is we have to write it clearly, that is for air m dot A SA at temperature T1 P1 plus m dot oxygen, and oxygen is at temperature T2 P2, this is the initial state, and final state will have m dot A air SA, and the final state is at temperature T3, and air is at pressure, that is its mole fraction into final pressure P3, plus m dot O oxygen, entropy for oxygen to be calculated at temperature T3, and pressure is the partial pressure of oxygen would be Y oxygen YO2 into P3 plus sigma dot is equal to 0. Okay, and this when you solve it, it gives the expression that sigma dot is m dot A SA T3 into Ya P3 minus SA at T1 P1 plus m dot O oxygen at temperature T3 YO P3 minus entropy oxygen at temperature T2 P2. So, this is nothing but delta S for air, and this is delta S for oxygen, and property value need to be evaluated, and this is equal to SA, or we say absolute value of entropy at T2 minus absolute value of air at T1 minus R bar by MA into ln Ya P3 by P1. So the term 1 is equal to this, term 2 will be SA means absolute value for oxygen O for at temperature T2 minus absolute value for oxygen at temperature T1 minus R bar by M oxygen into ln Y oxygen P3 divided by P1. So property data table needs to be evaluated. So this number is 1.77, this number is 1.71, these values are kilojoule per kg Kelvin, this value is 207 by 32 and this value is 213 by 32 kilojoule per kg Kelvin. So what we already know, Ma and Mo in our earlier data, P3 Ya we already know, P3 is known, P1 is known. So by inserting these values we get sigma dot is 17.4 kilojoule per Kelvin minute. So entropy production during this mixing process is 17 kilojoule per Kelvin per minute. So just to summarize these things, although you see these expressions are written, but you should understand the notation in which framework it is written. So based on the which it will be easy for you to calculate the property values directly from the book. So only it's a matter of inserting a data in a given equations, even though notations are looks little bit complicated, but if you are used to it, then it will be very easy to solve this kind of problems. Rather, the solution is just an addition or subtractions, but the way of representing in terms of notations normally takes time. Okay, with this viewpoint and understanding, and I will close this lecture for today, and also we close this module 4. Thank you for your attention.